My name is Demetrius Demetriadis, and I will present the paper, with title A Federated Approach in Training Acoustic Models. This is a joint work of Demetrius Demetriadis, Kenichi Kuminati, Robert G. Myr, Yashesh Gaur, and Sefik Emre Eskame, from Microsoft. In this paper, a novel platform for acoustic model training based on federated learning is described. This is the first attempt to introduce federated learning techniques in speech recognition tasks. Besides the novelty of the task, the paper describes an easily generalizable federated learning platform and presents the design decisions used for this task. Amongst the novel algorithms introduced is a hierarchical optimization scheme employing pairs of optimizers and an algorithm for gradient selection, leading to improvements in training time and speech recognition performance. The gradient selection algorithm is based on weighting the gradients during the aggregation step. It effectively acts as a regularization process right before the gradient propagation. This process may address one of the federated learning challenges, i.e. training on vastly heterogeneous data. The experimental validation of the proposed system is based on the LibriSpeech task, presenting a speed up of 1.5 times and 6% word error rate relative reduction. The proposed federated learning system appears to outperform the golden standard of distributed training in both convergence speed and overall model performance. Further improvements have been experienced in internal tasks. Differences between federated learning and distributed training lay in the assumptions made on the properties of the local data sets. Distributed training primarily aims at parallelizing local computing power, whereas federated learning focuses on training with heterogeneous data sets. Since distributed training focus is to train a single model on multiple nodes, a common underlying constraint is that all local data subsets need to be homogeneous, i.e. uniformly distributed and roughly about the same size. None of these constraints are necessary for federated learning. Instead, the data sets are typically heterogeneous, and their sizes may span several orders of magnitude. The federated learning provides a more flexible training framework, relaxing some of the constraints. To the best of our knowledge, a massively distributed and heterogeneous approach like the one presented here has not been applied before on speech recognition tasks. A sequence-to-sequence architecture is adopted for the particular speech recognition since the training of such all neural models is much more straightforward, all while being easier automating this process. Federated learning focuses on minimizing a loss function f corresponding to the global model W. As part of the FL process, this global loss function can be seen as a combination of local loss functions f of k over m devices. The contribution of each loss function is weighted with p of k. Each of the local losses contributes to the overall optimization of the model on the server. As such, gradients or models from the clients are aggregated in order to optimize the server-side model. The challenges for the optimization process include heterogeneous data, stale gradients, imbalance in the data and others. The contributions of this work are threefold. We first introduce a federated learning platform designed for horizontal usage. The platform is designed to be flexible, supporting different local and server optimizers, different model architectures, and use case scenarios. The second contribution is the hierarchical optimization scheme designed to reduce the communication overhead and improve the convergence speed. Finally, we propose a new algorithm for the gradient aggregation step, ensuring that batches of mismatched data are de-emphasized when aggregated together. Each of the algorithmic improvements is shown to provide an additive improvement in word error rate performance and convergence speed for training. Finally, it is shown that the performance of the speech recognition system is not sensitive to the number of working nodes included per iteration. Although there are many different architectures for end-to-end speech recognition models, we chose to use the sequence-to-sequence models with attention. As of lately, attention-based sequence-to-sequence models yield state-of-the-art performance in a range of speech recognition's tasks. The sequence-to-sequence model consists of three subnetworks, the encoder, the decoder, and an attention layer. Given the speech input samples X, the encoder first converts it into a sequence of high-level representations H encode. The encoder is a bidirectional LSTM with layer normalization. The decoder acts as an acoustically conditioned language model. The acoustic signal used for conditioning is summarized by the attention module before predicting a certain output token. For every decoder time step n, attention generates alignments alpha of n over the encoder output, and a corresponding context vector C of n. The attention layer is a location-aware attention. The model is trained with cross-entropy loss. In the presented experiments, a 6-layer bidirectional LSTM, with dropouts, is used for the encoder, 2 layers of unidirectional LSTM are used for the decoder, and finally, a conventional location-aware content-based attention layer with a single head is used for attention. The input features are 80-dimension log-mel filter bank energies, extracted every 10 milliseconds. 3 frames of features are stacked together and applied on the encoder as input. 16,000 subwords based on a unigram language model are used as the recognition units. The proposed system consists of a pool of K clients with a fixed data set per client. Contrary to distributed training, the training data is neither uniform nor reshuffled after every epoch. The data segregation remains fixed throughout the task. For the federated learning scenario, randomly sampled n out of K clients are processed in every iteration, T. The processed clients are then returned to the pool and can be picked again. It is shuffling with replacement. Using just these n clients without loss in performance provides additional flexibility unique to the proposed platform. Also, it ensures latency remains low since the server does not need to wait for many clients to return the gradients. Once these n clients finish processing data, the updated models, m tilde of j, are returned to the server for aggregation, and finally a global gradient is estimated. This gradient is used to update the global model, w of s, before the next iteration, t plus 1. Due to the sampling of clients, the sweeping of all data takes longer. However, the theoretical justification and the experimental results have shown that it is neither necessary for reaching an optimal point nor detrimental for the model performance. Initially, local models are trained on each of the working node. The starting model for each node is the server model WS at time step T1. At the end of the training iterations on the nodes, a smooth version of the gradient, G tilde of J, is estimated, as 1 gradient per node J. The smooth gradient is the difference between the starting model and the trained one. The J gradients are then weighted with alpha J as part of the aggregation step. The federated average is a subcase where all weights are equal. The final gradient is then used for updating the server-side model. The example here is using the SDG optimizer, but any optimizer can be used for both the training steps. Finally, a replay step on the server is introduced as a regularizer for the model. This replay step ensures that the model doesn't drift too far from the task in focus. Training with heterogeneous data poses additional challenges, especially for the aggregation step. In general, higher values for the training losses can be seen as an indication of batches that are not well represented by the model. Possible sources of such loss values are either data of bad quality, such as noisy data. Similarly, mismatch between the local training data and the model can lead to higher training losses. Finally, adversarial attacks or Byzantine nodes can create a similar situation with gradients very different than the expected. As a result, the aggregation process will become noisier due to this diversification of the aggregated models. Batches, where the training losses are of similar magnitude, would be expected to move the model in a similar direction, thus the aggregation process will be better aligned. Such alignment of the aggregated gradients is also beneficial for the convergence speed, as shown in the experimental section below. In any of the aforementioned scenarios, gradients that deviate from the rest should be processed differently. As such, the weights alpha of j can emphasize these adverse phenomena. The weights are the output of a softmax function with input all the training losses from the local training step. The idea is that bigger training losses are forcing the models to move further to a certain direction, while the rest of the clients have a more consistent training. So, the gradients with larger training losses should be de-emphasized. The causes of the training losses might be the quality of the data or the transcriptions, the mismatch between model and training data. The Libre speech task is used as the experimental testbed. The dataset contains about 1,000 hours of speech from 2,500 speakers reading books. Initially, a state-of-the-art sequence-to-sequence model is trained using Harovat on the entire training set of 920 hours. The performance of this model provides the lower bound of the word error rate since all the data is used in a centralized manner. For the federated learning-related experiments, the training is split into two parts of 460 hours of speech each, with no overlapping speakers. The first part is used to train a seed model, without ever using this data again. Then, the second part of the dataset is used to simulate online training, under the federated learning conditions. We will follow two different directions for the training process. First, the training set is split into 7 distinct parts without reshuffling the data again. The splits are random, with no overlapping speakers across them, but the data distribution is uniform. The second direction is to split according to the remaining 1,100 speakers. Each one, either 7 or 1,100, of the partitions is assigned to a client node. The clients are unaware of the rest of them, only the server knows which the clients are used, randomly sampling which of them will be aggregated. The best word error rate is 4% when the entire dataset is processed during training in a centralized manner. Next, we train a seed model for our experiments using only the first half of the data, and the resulting performance is 5.66% word error rate. As mentioned before, the first part of the dataset is not used again. The seed model is further improved by online training using the second part of the training data, and the end performance gets down to 4.66% word error rate. So far, all three models are trained in a centralized way till convergence. During federated training, the second half is split in non-overlapping chunks of data. We have investigated two scenarios, either splitting the data in 7 partitions or using 1,100 partitions, 1 per speaker. In the first scenario, the client data chunks are more uniform, whereas the second scenario ensures less uniformity. The more diverse scenario leads to better performance, although marginal. With the seed model trained on these segregated data partitions, the resulting model yields 4.45% when all aggregation weights are equal. Additional improvements in performance are yielded with the softmax weighting, with a relative improvement of 6% in word error rate. All models are trained till convergence, however different models and approaches require different number of iterations till that convergence. Herein, a novel federated learning platform for speech recognition tasks is presented. This is the first of its kind as far as the authors know. Although the discussion about the platform is focused on the task in hand, this platform can be easily generalized to other tasks. In addition to platform description, we are presenting novel algorithms addressing challenges unique to the speech recognition scenario. This novel approach of weighting the gradients between many batches allows for enhanced convergence speed UPS and improved model performance. The proposed gradient aggregation scheme acts as a regularizer, emphasizing batches where the data are not well modeled. Herein, a weighted gradient aggregation algorithm is described, enabling 1.5 times speed up and 6% relative reduction of word error rate on the Libre speech task. The future research directions include investigating privacy-preserving algorithms, gradient compression. Also provide refinements of the knowledge distillation methods. Thank you.